Wrong.
Well, there you have it. Video over. Just kidding there, guys. We are actually going to do a real video today. And just so you guys know where we're at, yesterday I published a video, and it was a quick video. I mean, it was from the range. It was real quick. It was not designed to be a full dissertation on the mathematics of external ballistics. And today is not going to be either, but I think we can get pretty close. So did you understand where we're at for this one? In that video, I had a Photoshop draw up that I did really quick of the commonly accepted approximation curve for a trajectory. It was not drawn to scale. It was just something that I threw together in 5 minutes in Photoshop. Okay, so that all said. We're going to get to the meat and potatoes of that here in a second. But a lot of people, from reading the comments, basically jumped all over the diagram and said how it was wrong and how it should be correct because I'm a teacher and all that. Whatever. So what we're actually going to do is look at why that curve is fine for what we're talking about. Basically, what people were arguing is that the bullet does not do this. And actually it does do that. But the reason it does that is not because of what they were describing. Describing a physical phenomenon, and we want the truth about it, we need to have an understanding of the underlying concept and the math that governs it. And we could also write that another way, which is basically the truth is equal to the algebra plus the trig plus the calc. And for anything that I care to discuss on a YouTube video, we can pretty much eliminate the calculus, and that's going to get us 99% of the truth. So as you can see, we're already talking about an approximation of the truth. And basically what that eliminates is things like, in this particular instance, when we're talking about external ballistics, that eliminates Magnus effect, that eliminates spin drift. In this particular instance, and most people do this anyway, we're not going to take into account air resistance and things like that. So we're going to eliminate everything that basically the BC of the bullet is concerned with. Now for this demonstration, you guys can see that I have a rifle here on the wall, and basically I did not measure this before this video, and it doesn't really matter because we're going to use AR anyway. But you can see here that we have an optic and a barrel optic, and you can see that these are clearly not on the same plane. Okay, and this is not level, and we're actually going to use that to our advantage. It can move around. What they said, and they're correct about, for the most part, is that the bullet is going to exit the barrel along the axis of that barrel. So if the barrel is point A to point B, we have a vector, basically, and that bullet is going to leave along the straight line. I don't know if that's straight relative to the camera, but it's going to leave going in a straight line. And we understand this. That, for instance, is the mathematics that we use to calculate energy from basically what the bullet is doing from point A to point B through a chronograph, and then we use the mass and basically create the approximation of the kinetic energy that bullet is going to deliver at the muzzle. However, we know that this is not the truth, and we know that we have the first number that we need to talk about, which is gravity, which is 9.8 meters per second squared acceleration towards the Earth. And what that means is that this is going to curve downward at a progressive rate. So in that video, though, we were talking about a target at 25 yards, and this does not really apply because the bullet is not going to, compared to the rest of its motion, make an appreciable drop between 25 yards and the barrel. It's just too short a distance. The bullet is moving too fast. So if we're talking about 5.56, for instance, we're talking about something that's going 2,600 feet per second. If we convert this to meters, then this is going to be something like 790 meters per second. You know what? I should look that up on my phone. I should do a calculation really quick. Okay, so there you have it, 792 meters per second. That was pretty close. So this is, again, another approximation, but before we receive a full gravitational effect on the bullet, we've moved 2,600 feet per second. So before we've changed the negative velocity of the bullet towards the Earth by 9.8 meters per second, we have moved 792 meters. So basically the purpose of this was to show you that basically, as far as we're talking at a 25-yard target, the bullet drop to gravity is going to be almost zero. It's not going to matter. It's not going to govern this. Now, gravity will take over later, but for the sake of the discussion for what I'm about to get into, basically what we can say is that from the end of the muzzle to the target at 25 yards, it's, for all intents and purposes, a straight line. So the fundamental miss that everybody who is discussing that in the comment section perpetrated, so the wrong here was the assumption that the barrel is level with the optic. Okay, so these two lines, the line of sight of the optic and the line of sight of the barrel, are parallel lines, and that is not the truth. So we can see that this is very easily true by drawing a ray from the barrel to the target at some arbitrary distance and a ray from the optic to the target. If I'm trying to hit here by aiming at it, if these two are set up to be level, there is no way that I can look through this and hit there with the barrel that is parallel to the optic. It just cannot happen. It physically cannot happen. So what we do is we make an adjustment on the optics back here that changes the relationship between the barrel and the optic. And what we do is we actually change the point of aim down of the optic so that it meets at some distance. So our line of sight, where the reticle is, ends up pointing at where the barrel is at some particular distance. And what that allows us to do is drag the trajectory of the bullet upward to where we want the bullet to hit. So the best way that I've ever seen this done in popular culture to describe bullet trajectory is actually the grenade reticle in Gears of War, the video game. I mean, they do an excellent job of, just immediately describing how projectile flight works. Now, we can get into a whole dissertation on how video games do bullet mapping and stuff like that. But what we're talking about here is physically dragging the arc of the bullet into a different place. So if we take the inverse of this, what we're actually talking about is where our eye ends up. So eye and reticle form a straight line that go to some point off in the distance. And now we've changed the orientation of the barrel to the target. And that is what actually causes this bullet to create this arc. Again, not accounting for gravity in this particular instance, we would fire this gun and we would get, if this was an AR-15, we would get a vertical displacement of approximately 2.7 inches between the two of them, because the bullet would fly in a straight line and the optic would be pointed in a straight line. We would hit pretty much exactly 2.7 inches low of our point of aim, and that would mean that the two are parallel. If we want to make a hit, a perfect hit at 25 yards, then we have to change this in some degree. We have to raise the barrel up by dropping the sight down. So if we do some quick math, 25 yards equals 900 inches. We then see very quickly that if we take this away, right here, we end up with a triangle, and that is the worst triangle that I've ever drawn in my entire life, but you guys get the idea. See, I care about you guys. I took the time to redraw it real quick. So that means that this leg is 900, and this one is 2.7. Of course, this is 90 degrees. And now, guys, look, this is pre-calculus, right? This is trigonometry type stuff. And we end up with a theoretical barrel angle of 0.17 degrees. Okay, so I've redrawn this to give us a little bit more room to speak. Again, uniform theme here, not to scale. If we know the angle of attack, if you will, the angle of departure, I believe it's usually called by people who actually are really good at shooting long range. If we know the angle of departure, then we can use this to calculate, at least in a roundabout fashion, again, approximation, 29%, the component vectors of the velocity. So if we just use 2,600 feet per second as the measured velocity at the chronograph, and I will admit that I used a calculator to do this one, unlike the other one, we get a component horizontal velocity here, and at least as far as this is concerned, horizontal, of 2,599.9 feet per second, and a vertical component of 7.7 feet per second. So if we remember back to our 9.8 meters per second squared downward towards Earth, we have something to combat here. So right out the barrel, we don't end up with a flat and straight. We have to deplete some of that vertical velocity back down with the acceleration due to gravity. So what that results in is that this bullet, before gravity gets it back down because it's going so quickly, ends up flying off into the distance. Okay, so we're going to say we got a target right here at 25 yards approximately. If we fire this round at that angle, that 0.17, it's going to strike the target, and it's not going to just stop doing anything then. It's going to continue on for a certain amount of time. Now, remember that all the time, gravity is pulling this down. So instead of a perfectly straight vectored line right like that, we're going to have something that starts to do this. Eventually, gravity will fully take over and return it to Earth. But if we look at our line of sight here, it looks like this. So we come above the line of sight. The bullet goes above the line of sight because it's being fired there, and then it comes back down to Earth. In an AR, if we used a 25 meter zero, for instance, for a 5.56 round, we're talking about 10 inches here. So what I'm going to do right now is I'm going to go ahead and take the original diagram. And are you ready? And now we've done the correction with the correct angle so that it's all correct, if you will. Again, not drawn to scale.
That's correct.
So the reason we use this approximation trajectory, if you will, that I used in my initial diagram is because it helps people, okay? These are not laser beams that fire in a straight line for infinity, and presenting this classical arc of a bullet, if you will, to someone helps them wrap their mind around that concept that physics affects these things when they fly down range, and it gives them an informed perspective on how that bullet is going to perform when it leaves their barrel. It can also help you at more advanced levels know when your equipment is lying to you. It's a uniform concept in science. You have instrumentation that gives you data, and the bullet does not lie. So if you input your ballistic calculations ever so slightly incorrectly, and you fire the bullet and it's way off, you know that you screwed something up in the process. And having that concept in your mind of basic mathematics as far as this is concerned can help people. So if you put it in and your ballistic computer or your pen and paper gives you a result that's the wrong sign, that's telling you to move it in the wrong direction, if you understand this concept, you know that you screwed something up along the way, and you can rectify that situation before you turn the dial the wrong direction and send a bullet over the horizon. Anyway, guys, I hope that you learned something from this video. The bullet absolutely will rise above the line of sight if the gun is properly zeroed. Proof of concept, guys, and these are pretty popular in the shooting, long-range shooting community. They sell bases that grow this deviation between the angle of departure of the bullet and the line of sight of the optic. And these are commonly referred to as 20, 30 MOA bases. It's the measurement of offset in the base that you get just by mounting a scope on top of it. You get a change in angle, and you can think of it as a wedge is literally being shimmed underneath of the optic that changes its perception relative to the barrel. And what that does is it can take a scope that may not have the adjustment to shoot out to the desired range. You compromise that ability to shoot the super short range for the ability to change the bullet trajectory to enough of an extreme angle to be able to hit those targets way downrange. So it's a trade-off. I hope that you guys learned something here today in this video. If you guys did, absolutely be sure that you like and share the video. Hopefully you can show this to some of your friends that maybe have a misconception on how bullet physics works, ballistics works, excuse me. I would greatly appreciate if you guys enjoyed the video, and if you did learn something, that you would smash that subscribe button down below and make sure you turn on those notifications so that you'll know next time I have a silly idea for a video.